So we're going to talk about heat capacity for gases this time. If you remember when we talked about heat capacity for solids, or really liquids also, we said Q equals mc delta T, where this was the specific heat capacity. Right. And so we could write C is equal to Q over m delta T. If you recall, I said at that time sometimes you're interested in the molar heat capacity. So this is the heat capacity per mass. Right. And so we can write that this way. We can say, look, Q is equal to the number of moles times the molar heat capacity times delta T. Right. So that's the heat capacity per unit mass is called the specific heat capacity, right? That's what this is. Sorry for all the arrows. But this is called the molar heat capacity. This is joules per kilogram per mole Kelvin times the number of moles times the temperature. It gives you the number of joules. And so this is just another way of sort of looking at the same thing. Here you're seeing how much heat it holds per mole. Here you're seeing how much heat it holds per kilogram, essentially. And so for gases, we usually either keep volume or pressure constant. That is to say, if you have a gas and you start adding heat to it, and you talk about its ability to hold heat, well, if you're allowing it to expand, let's say it's in a balloon, if you're allowing or a tube with a piston on top or something, if you're allowing it the gas to expand while you're adding heat to it, by expanding it's doing work on whatever it's expanding against it, so it's using up some of that heat to do work, and that's kind of cheating. That's kind of letting energy get out of the system. And so sometimes you'll either want to look at CV, which is the molar heat capacity at constant volume. Sometimes you're interested in the molar heat capacity at constant pressure. And this is for gases usually. For liquids and solids, there's not much change in volume. Liquids and solids, as long as they aren't phase changing, which they're not in these circumstances, in these equations, you're not worried about volume change because they're so fractionally small. And so it's only for gases that this one matters. And so we'll start first by talking about the heat capacity at constant volume. And so we can say for this one, Q is equal to N times CV times delta T. And so since the volume is constant, and we assume that the gas isn't able to do changes chemistry or anything like that, that all of the heat is going into all the internal energy is going into changing the temperature. And so we can say the change in the internal energy, right, is equal to the heat added if the volume is constant. Okay. And so if you remember, for a gas, the change in internal energy is equal to 3/2 nR delta T. Right? That's what we calculated earlier. And so that means 3/2 nR delta T is equal to NCV delta T. And so if I just come back up here, I know I probably should do this, but so when you say Q is equal to the change in the internal energy, right? This guy is equal to that guy is equal to that guy. That means that N times CV delta T is equal to 3/2 and R delta T, right? The delta T's cancel, right? The N's cancel. And we get, for a gas held at constant volume, the molar heat capacity is 3/2 R, right? And that's just a universal gas constant. So any ideal gas has a molar heat capacity at constant volume of 3/2 times R. So a sample of neon, this is a gas, right, the noble gas, with a molar mass, which has a molar mass of 20.2 grams per mole, is at 13 degrees C. It's put in a steel container. The mass of the container is 47.2 grams. You can assume that no heat gets outside the container, so the system of the neon and the steel is isolated. And the container is at minus 40 degrees C. So the neon's poured in, the container is at minus 40, that's the mass of the container. It says the final temperature of the neon plus the container is minus 28 degrees Celsius, and it says what's the mass of the sample of neon. And so in this problem, this is a calorimetry problem, right? And basically, since the system is isolated, that is to say the container and the neon, we can say, look, Q for neon plus Q for the steel is equal to 0. In this case, the steel's going to warm up and the neon's going to cool down, but the heat gained by the neon is exactly balanced by the heat gained by or lost, if you will, by the steel. And so the way we write these is, since this is a steel container and it's got a fixed volume, we'll use the volume equation for this guy, the constant volume. And so we'll say, look, the number of moles of neon, I'll just call it big little n for number of moles, big N for neon, times heat capacity at constant volume, right, which is 3/2 R. We've already said that for gases. Anyway, for monatomic gases, but we'll get to that. Times delta T for the neon, plus, so the steel container just goes back to the old way. We can just say mass of the steel times the specific heat capacity for the steel times delta T for the steel is equal to 0. Heat gained by the neon, heat gained or lost technically. Sorry, this guy's going to gain heat, this guy's going to lose heat, adds up to 0. They're asking us for the mass, and there's no equation for the mass of the neon, but if you remember, the mass is equal to the number of moles times the molar mass. So we're going to calculate the molar mass of the neon and we're going to calculate the number of moles of the neon multiplied by the molar mass at the end, and that'll give us the mass of the neon. And so I can well, let me just write down a few things here. So we already said that CV, we already know that. Again, this is the molar heat capacity at constant volume, right, is 3/2 times R, right, where R is the universal gas constant. It's 8.314 joules per Kelvin mole. So that's CV. Delta T for the neon that's its initial temperature, that's its final temperature, so it's minus 28 degrees C, minus 13 degrees C, right, final minus initial, that's 41 degrees C, and it's negative, right, negative 41 degrees C, right. The specific heat capacity for the steel is 452 joules per kilogram time degree C, or Kelvin. Again, they're temperature differences, so it doesn't matter. And then finally, delta T for the steel is the final, which is minus 28 degrees C, minus the initial, which is negative 40 degrees C, which is 12 degrees C. And so now I can just solve this equation for N, and I can say, look, the number of moles of neon is equal to, so it's negative M sub S, C sub S, delta T for the steel, over the heat capacity at constant volume, molar heat capacity at constant volume for an ideal gas, times the temperature change for the neon. And so I can just start plugging in at this point because I want this the number of moles. And so it's negative. The mass of the steel is 0.0472 kilograms times the specific heat capacity for the steel, which is 452 joules per kilogram degrees C, times the change in temperature for the steel, which is 12 degrees C, all over 3/2 times the ideal gas constant, which is the universal gas constant, which is 8.314 joules per, if I want to, I can say degrees C mole. Usually we have Kelvin, but since I put the temperatures in degrees C, times the temperature change for the neon, which is minus 41 degrees C. And what I get when you cancel all these units is about 0.5 moles. Right, the joules cancel. I can go through and start canceling stuff. The kilograms cancel, the degrees C's cancel, degrees C's cancel, and all I'm left with is a mole, and that comes up here. And then I can get the mass of the neon is equal to the number of moles of neon times the molar mass, which is 0.5 moles, times the number at the very top there, 20.2 joules per mole. Kilograms per mole, sorry, grams per mole. I got carried away with my joules. And so it's equal to 10.1 grams. Hopefully that's all on there. So when we're deriving the kinetic theory of matter, one of the results was that we said 1/2 mvx squared, sort of the average, was equal to 1/2 kT. And then we said, but really, that was just the x component. The average, the average of the squared velocity, the total velocity, is vx squared plus vy squared average plus vz squared average. The averages are just a little ugly. We have to remember that these are distributions of gas molecules, and we're kind of just picking an average on those. And so that means if there's no preferred direction, then that means you can just say that v squared is equal to 3 times any one component squared, something like that. And so then we would say, look, the total kinetic energy, 1/2 mv squared, is 3/2 kT, and that was kind of the argument we made. And so really what we're saying is there's a 1/2 kT for each degree of freedom. It can move in the x direction, in the y direction, and the z direction. And so we say 1/2 kT of energy per degree of freedom. And this is really called the equal partition theorem. That is to say, for every degree of freedom a molecule has, it can dump a 1/2 kT into that. So if it can only move in the x direction, it can get a 1/2 kT. If it can move in a plane, it can get kT. If it can move in 3 dimensions, it has 3/2 kT. And now we sort of generalize this statement to look at things that aren't just points anymore. So for example, if you look at a nitrogen molecule or any diatomic molecule, you have 2 molecules separated by a distance, right? And so I'll just pretend that that's a pin, that this pin is that molecule, and it's got a, you know, if it's like oxygen, it's got an oxygen here and an oxygen here, and they're kind of stuck together. And so then, in addition to being able to move around in 3 dimensions, it can also store energy by spinning. And an object that's got a sort of fixed separation here, it can either rotate this way in this plane, or it can rotate in the vertical plane this way, right? We don't count this one because it's, in the ideal sense, it's got no radius this way. The nuclei are infinitely small, so it can store energy this way and this way. So it gets two more degrees of freedom. And so a rigid diatomic molecule has 5 degrees of freedom. And that means that the molar heat capacity at constant volume is not 3 halves R, it's 5 halves R. Now, actually, diatomics can also vibrate. These molecules are not rigid, they're not fixed in place. They can also move back and forth this way. And so as they're going around or spinning or moving, they can be oscillating this way, and they do once they get above a certain temperature. And so that vibration, which can only happen along the axis, along the direction of connecting the two nuclei, actually adds 2 degrees of freedom. There's one for the kinetic energy of the molecules as they're vibrating back and forth, but there's also a potential energy that occurs because it acts like a spring between them. And so if we include vibration, CV is equal to 7 halves R. And so if I go all the way back to the equipartition theorem, the equipartition theorem really says the molar heat capacity at constant volume is equal to D over 2 times R, where I'll just write it down here, D equal number of degrees of freedom. It turns out that whether or not a molecule can rotate or vibrate as it moves depends on its temperature. And so even diatomic molecules, which you would think could rotate at any temperature, can't. And so at very low temperatures, a diatomic molecule acts like a single atom and just has a molar heat capacity of 3 halves R. A molar heat capacity at constant volume of 3 halves R. As it warms up, the rotational states become available, and it can go to 5 halves R. And as it gets even hotter, and now we're talking about maybe 1,000 Kelvin or something, it goes to 7 halves R. And so which of these is available depends on the temperature, and so if you're working a problem on these, it would have to tell you how many states were open, how many degrees of freedom were available. So if it's a monatomic gas, a single atom gas like helium or neon, you'll see those things in our homework problems. That's saying that's telling you that the degrees of freedom is 3. A single atom doesn't rotate or vibrate or anything like that. It has to become a molecule before you can get these other degrees of freedom. And so if it's a molecule, it might say acts like a rigid diatomic molecule or something like that. So in this problem, we're talking about heliox, which is a mixture of helium and oxygen, which is sometimes given to patients who have trouble breathing because helium is lighter. So it's just a lower mass. Air is 80% nitrogen, and so that's a heavier gas. So it's easier to breathe a heliox mixture than it is to breathe air. And all you really need is the oxygen, so that's why they do that. And so in this problem it says, suppose the helium is at 25 degrees and is mixed with oxygen at 35 degrees, so that the mixture is 70% helium by mole. And it says, what is the final temperature? And we're assuming the final volume is equal to the sum of the 2 initial volumes, so that you can kind of treat it as a constant volume thing. That is to say, you have a partition, you just remove it, and so they still are sort of occupying, you might say, the same amount of volume, even though they're stretched out through a mixture. And so this is, again, a heat capacity problem, a calorimetry problem, where we say, Q for O2 plus Q for helium. I'll just use O and H is 0. That is to say, the helium's cooler, so it's going to gain heat from the oxygen, which is warmer, and we want to know how they're going to mix. And the reason it's complicated is because they don't have the same heat capacity per mole, because at 35 degrees C, And you can look at the table on page, the chart on page, I'll have to look it up real quick, 93 of your book, or you can just Google molar heat capacity of molecules, and you'll see that at room temperature, the degrees of freedom for oxygen, O2, is 5, and of course helium is monatomic, so it's got 3 degrees of freedom. And so, you know, CV for oxygen is 5/2 R, and CV for helium is 3/2 R. And so when we solve this problem, we get the number of molecules of oxygen plus times CV for oxygen times delta T for oxygen plus the number of moles of helium times CV for helium times delta T for helium is 0. And you kind of have to recognize, I guess, that we don't have a fixed volume here. All they're telling us is the proportion. And so we can just say, look, this is going to be 0.7 and this is going to be 0.3. They could be times something, but you would just divide that out. And so if I get the proportion right on these things, I can just do, you know, fractions of 1 mole, and I can say that's 0.7 moles and that's 0.3 moles. And so this would give me, I can write this as 0.3 moles, that's for my oxygen, times 5/2 R, times, if I want, I can say T final minus T oxygen initial, right? T final is the final mixture of the pair. They're both at the same temperature, so I don't have an oxygen here. This thing is at 35 degrees, right? Plus 0.7 moles times 3/2 R times T final minus T helium initial, and that's equal to 0. All right, that's just rewriting this. Notice I can cancel the R's. There's a 0 on this side, I can just divide through by R. This is, I can also multiply through by 2 and cancel the 2's out, right, just to make my math a little simple. And this becomes 1.5 moles times T final minus 1.5 moles times T oxygen initial plus 2.1 moles times T final minus 2.1 moles times T oxygen initial equals 0, right? And so I just want to solve for T final, and so I'm going to add those two guys up. I get 3.6 moles times T final equals, I'm going to move the negatives to the other side, 3.6, sorry, no, I can't do that one. This is 1.5 moles times T oxygen initial plus 2.1 moles helium, correct that in a second, moles times T helium initial. So that should have been the initial temperature of helium. That was this guy, right? These two guys, the oxygen guys. These guys, the helium guys. I moved the negatives over to the other side. So that's the oxygen initial. That's the helium initial, and so then T final is 1.5 moles. I can cancel out all the moles if I want to, the moles unit, right? And I can get it's 1.5 times T oxygen initial, which is 35 degrees C, plus 2.1 times 25 degrees C, all divided by 3.6. And so what I get for T final is, comes out to like 29.2 degrees C. So it's a little tricky. We have different degrees of freedom here. These are just sort of my standard heat capacity of a gas at constant volume equations, and I just have to be careful that This guy has a higher heat capacity because the oxygen can store more energy per mole by spinning and rotating than the helium can, because all it can do is move. Nevertheless, the temperature ended up a little closer to helium's temperature because there was more than a factor of 2 more helium, right, than there was oxygen.